welcome to the Deep Dive. Today, we're really digging into a stack of sources all about radiography principles and digital imaging equipment. Think of this as a focused review session, okay? We're hitting the highlights for that RT 304 final exam material.
That's right. We're going to unpack the core concepts, everything from how X-rays get made to how we capture them digitally, and importantly, what really affects your image quality. Basically, we're hitting the stuff you absolutely need to nail down.
Yeah, our goal here is to highlight the key facts, show you how different concepts connect, and maybe point out some little things that are super crucial for understanding, stuff that's likely to show up on exams, obviously, but also stuff you'll use every day in clinical practice. We want to make this material stick.
Exactly. Let's get into it.
Okay, let's maybe start with the image itself, specifically the digital side, because, well, that's pretty much where modern radiology is at. So when we talk about seeing those tiny details, spatial resolution, what's the thing in the detector that ultimately limits how good that resolution can be? Like the physical bottleneck.
Yeah. The sources are pretty clear on this. The ultimate limit for spatial resolution in digital imaging, it comes down to the size of the DEL, the detector element. Think of it as the smallest little sensor that can grab information. Its size sets the absolute limit on detail.
The DEL. Got it, like a tiny pixel bucket. And speaking of pixels, the source gives an example matrix size, 2048 by 1536. So if you have a detector with that matrix, just how many pixels are we talking about?
Yeah, that specific one, let's see, it's 3,145,728 pixels. It's a lot of little squares making up the image you see on the screen.
Wow, over 3 million.
Yeah.
Okay, and the source points out something interesting about pixel size, kind of a trade-off. It says, reducing pixel size actually increases patient dose, which sounds bad, but what's the upside? What good thing happens to the image if you use smaller pixels?
Well, the upside is you get better spatial resolution. Smaller pixels mean you can see finer details more clearly. So yeah, you get better detail, but it costs you in terms of dose. It's one of those constant balancing acts you deal with in imaging. The sources really emphasize that.
Absolutely, a balancing act. Okay, so how does the system actually capture the X-ray energy? Let's think about indirect capture DR first. The sources say there's a step where the X-ray energy gets converted into something else before it becomes electricity. What is it?
Right. In indirect capture, that absorbed X-ray energy is first turned into visible light.
Visible light. Okay. And what's the detector material that actually senses that light in indirect capture?
That would be amorphous silicon. It's a semiconductor, and it's good at detecting that light signal.
But the sources add a bit more detail about the very first step. What's the specific material, the capture element, that does that initial X-ray to light conversion?
Yeah, good distinction. That first part is cesium iodide. It acts as the scintillator. It actually glows when the X-rays hit it. That light then goes to the amorphous silicon. So you've got cesium iodide as the capture element, amorphous silicon as the detection element, for indirect anyway.
That difference is key, yeah. Now, let's switch to direct DR. The sources say direct DR skips the light step altogether. X-rays straight to electrical signal. So what component in direct DR collects those charges created by the X-rays and makes the signal?
That job falls to the TFT, the thin film transistor. The sources mention the TFT as one of the collection elements that gathers the signal.
And the sources list a couple of other things in that same category, right, besides TFT.
They also list CCD, which is charge-coupled device, and photodetector as other types of collection elements you might find in digital systems. Good to know those terms.
Okay. Stepping back just a bit, one really big difference the sources point out between digital radiography, DR, and the old film systems is, well, the receptors are reusable, right?
Huge difference, practically environmentally. Yeah. Reusable receptors are a defining feature of DR.
Okay, so once you have the digital image, how do you know if your technique, your exposure factors, were actually any good? What number do you look for? Right, that's where the exposure indicator number comes in. The sources really stress this because digital is so flexible you don't get those obvious visual cues like dark or light film.
Yeah.
This number tells you if you hit the target range for dose and quality, you'll be checking this constantly. Definitely something to watch in the lab.
And let's loop back quickly to matrix size. The sources confirm what we said earlier. Spatial resolution is improved with a bigger matrix size. More pixels packed into the same area just means more detail.
Here's a little historical tidbit from the sources. Scan projection radiography. Apparently it was developed as a complement to another big imaging modality. Any idea which one?
Oh, interesting. Yeah, the sources say it was developed alongside computed tomography, CT. Shows how these technologies often push each other forward.
Okay, good stuff on digital receptors. Let's switch gears and go right back to the source. Literally, inside the X-ray tube. Thinking about the cathode assembly, where the electrons start, The sources list parts: filament, focusing cup, stator. Which one is not actually part of the cathode assembly?
Ah, okay. Based on the source descriptions, the stator is the odd one out. The stator is part of the anode assembly, specifically for rotating the anode, and it's outside the glass tube. Filament and focusing cup. Definitely inside, definitely cathode.
Perfect. So inside the cathode, you heat that filament, electrons boil off, thermionic emission. But the sources describe this kind of self-limiting effect, where the cloud of electrons already there pushes back against new ones trying to leave. What's that called?
That's the space charge effect. It's a really fundamental thing for understanding how tube current, the MA, is controlled. That cloud builds up and kind of limits further emission.
So cathode basics, filament focusing cup. What's the main job, the primary purpose of that whole cathode structure?
Its main job is to produce that thermionic cloud. You heat the filament, electrons boil off. That cloud is your source of projectile electrons that will fly across and hit the anode to make X-rays.
And that focusing cup, the sources mentioned its electrical charge. What is it?
The sources say the focusing cup has a negative charge, which makes sense, right? It repels the negatively charged electrons in the cloud, helping to shape them and aim them towards that small focal spot on the anode.
Right, focuses the beam. Filaments are usually tungsten, high melting point, obviously. And most tubes have two filaments. Why is that?
Yeah, most diagnostic tubes have two to give you two focal spot options. Usually a small one for better detail and a large one for techniques that generate more heat.
Okay, so when would you typically choose that large filament, the large focal spot?
You'd go for the large focal spot when you're using a high MS technique, maybe for a thicker body part. The heat load is high, and maybe superfine detail isn't the absolute top priority. The larger spot just spreads the heat out better on the anode target.
Now, the sources also mention some radiation doesn't come from that nice, intended focal spot. What do we call radiation made up of photons not produced right at the focal spot?
That's called extrafocal radiation, or sometimes off-focus radiation. It's basically scatter generated within the tube, and it's not great because it can contribute to image blur and increases patient dose slightly.
Speaking of unwanted radiation,
Yeah.
the tube housing is lead-lined for safety. The sources give a very specific number for the maximum allowable leakage radiation.
Right.
What is that limit? You absolutely have to know this one.
Yeah, this is a critical safety standard. Leakage radiation must not exceed 100 millioennigens per hour, MRHR, measured at a distance of 1 meter from the tube housing. Definitely memorize that number.
Okay, zooming out again. The whole system. What are the three main principal parts of a complete X-ray imaging system, according to the sources?
The big three are the X-ray tube assembly itself, the control console where you set your factors, and the high voltage generator that powers the whole thing.
Got it. Tube, console, generator. All right, let's dive into the physics. How X-rays interact with matter, how they're made. The sources talk about different ways X-rays behave when they hit the patient. At high kVp, say 125 kVp, what do most of the X-rays actually do?
Well, at those higher kVp levels, the sources say most X-rays are actually transmitted right through the body without interacting at all. The sources also mention, kind of generally, that only about 1% of the beam gets transmitted without interaction overall. But the key point for high kVp is that the proportion of transmission goes way up.
And those transmitted X-rays, they're the important ones for the image, right? The sources say they contribute the useful information. The pattern of transmission creates the image contrast.
Exactly. The ones that make it through are the heroes. Now, back at the anode target, when those fast electrons slam into it, most of the X-rays that get produced happen through one specific interaction. What's it called?
That's Bremsstrahlung, often just called Brems. That's where most of your X-ray photons come from.
And can you give us the quick rundown? What happens during a Bremsstrahlung interaction according to the sources?
Sure. The sources explain that a projectile electron from the cathode flies past the nucleus of a target atom, like tungsten. The nucleus is positive, the electron's negative, so there's a strong attraction. This force makes the electron slow down and change direction. That loss of kinetic energy is given off as a Bremsstrahlung X-ray photon. The key, the sources say, is slowing electrons.
Right. So when that Brems photon is emitted, what kind of energy got converted?
It's the electron's kinetic energy of motion being converted into electromagnetic energy, the X-ray photon.
Okay, Brems is the main one. But the sources also talk about characteristic X-rays. These are different, involving electron shells. For tungsten, which shell interactions produce the useful characteristic X-rays for imaging?
For tungsten, the useful ones come from K-shell interactions. The sources explain it generally. An inner shell electron gets knocked out, and an outer shell electron drops down to fill the hole. That energy difference between the shells comes off as a characteristic X-ray.
And the sources give a calculation example. Let's say an M-shell electron fills an L-shell vacancy. If the L-shell binding energy is, say, 26 keV and the M-shell is 4 keV, what's the energy of the characteristic photon produced?
You just subtract the binding energies. So 26 keV minus 4 keV, that gives you a 22 keV characteristic X-ray. The sources want you to understand that energy difference calculation.
Okay. Now, back to those electrons hitting the target. They have a ton of kinetic energy. We get some X-rays, sure, but what happens to the vast, vast majority of that energy?
Yeah, it's mostly wasted, unfortunately. Most of that kinetic energy just gets converted into heat at the anode. The sources even point out most of the heat comes from just exciting outer shell electrons, not even the interactions that produce the X-rays we want.
Explains why anodes get so hot and need ways to cool down. Okay, let's think about the X-ray beam itself, the emission spectrum graph. How does changing the kVp affect that graph?
Increasing kVp does two big things. It increases the amplitude, makes the curve taller, meaning more photons overall, and it shifts the whole curve to the right, meaning higher average energy, more penetration.
And what about increasing MAs? How does that change the spectrum?
Increasing MAs only increases the amplitude. Taller curve, more photons, but no change in the energy range or the peak energy, just more quantity. That difference between kVp and MA's effects is really important to grasp.
Absolutely. Quick true-false from the sources. Increasing X-ray tube filtration increases X-ray quantity. True or false?
That's false. Filtration increases beam quality or hardness by removing the low-energy photons, but it actually decreases the quantity, the overall number of photons. It hardens the beam, reduces dose, but lowers intensity.
Good clarification. Okay, let's shift to image quality itself and how exposure factors tie in. The sources list two main characteristics of any medical image we're trying to optimize. What are they?
The two big ones are spatial resolution and contrast resolution.
And how did the sources define those? What's spatial? What's contrast? And didn't the sources mention something about human vision too?
Yeah. Spatial resolution is seeing two small things that are close together as separate. Contrast resolution is being able to tell the difference between tissues with similar densities, like gray matter and white matter. And yeah, the source mentioned the human eye can only really distinguish about 30 shades of gray on its own, which is why digital processing helps so much.
Exactly. We need those tools. Speaking of digital metrics, the sources mentioned DQE. What's DQE stand for again?
DQE is detective quantum efficiency.
And what's it actually measuring? What does a good DQE tell us about the system?
DQE basically tells you how efficiently the detector uses the X-rays it receives to create a good, low-noise image. Like how much signal it gets for the radiation it absorbs compared to a perfect detector.
Higher DQE is better means potentially lower dose for the same image quality.
Okay, improving contrast resolution. The sources list a few ways to do that. What are they?
Let's see. The sources mention patient compression, using tight collimation, and lowering the kVp. So if you saw those as options, the answer would likely be all of the above based on this material. Lowering kVp is a big one for increasing contrast, though it affects dose too.
Right, let's talk dose again. True or false, based on the sources. Using low kVp with high MAs is a good way to reduce patient dose.
That's false, according to these sources. High MAs generally means higher patient dose. The usual goal for dose reduction is to use the highest kVp you can get away with for sufficient contrast, which lets you lower the MAs.
Okay, now for some really practical rules. Technique conversions the sources highlight. These are gold. The 15% rule. If you increase your kVp by 15%, how much can you reduce your MAs by and still get roughly the same exposure to the receptor?
That's the classic. 15% kVp increase means you can cut your MAs in half a 50% reduction and maintain exposure. Super useful rule of thumb.
And how does that 15% kVp increase compare to just doubling the MAs in terms of the effect on the image receptor exposure?
The sources say they have about the same effect. Both will significantly increase the signal hitting the detector. Really shows how much punch kVp has.
Okay, simple question. If you only want to change the beam intensity, the quantity of X-rays, but leave the penetrability alone, what factor do you adjust?
That's MAS. If you just need more or less signal, change the MAs. The sources state clearly there's a direct relationship between quantity and MAs. Double MAs, double the photons. Simple as that.
The sources give an example technique. 65 kVp, 300 mRMA at 0.1 sec. That works out to 30 MAs. Why would that specific technique likely give a higher patient dose compared to achieving the same IR exposure with a higher kVp and lower MAs?
Because at 65 kVp, the beam isn't very penetrating. A lot of photons get absorbed by the patient and don't make it through. So to get enough signal at the detector, you need to start with a whole lot more photons, high MAs, which means more get absorbed, increasing patient dose.
Makes sense. Let's touch on generators quickly. Compared to an older system like half-wave rectification, what effect does using a three-phase generator have on the X-ray output?
A three-phase system gives you a higher quantity of X-rays. The voltage is more consistent, so you're making X-rays more efficiently throughout the exposure time. And the sources add that practical note. You, the technologist, can't change the generator type. That's fixed when the room is built.
Good point. Now, distance. Always important. Inverse square law time. The sources give this scenario. Intensity at 180 centimeter SID is 0.02 milgi. What happens to the intensity if you cut the distance in half, down to 90 centimeter SID?
Okay, inverse square law. Halve the distance, the intensity goes up by the square of the distance factor. So distance ratio is 1 I0 unzar 90 equals 2. Square that, you get 4. Intensity increases by a factor of 4, so 0.02 milligia times 4 equals 0.08 milligia. Good to know the inverse square law.
Absolutely. What single factor primarily increases the beam's penetrability, its ability to get through stuff?
That's KEVP. Higher KVP equals higher energy photons equals more penetration.
All right, let's move into scatter, grids, and geometry. Scatter, the enemy of contrast. According to the sources, what are the three main things that influence how much scatter you get?
The big three are KVP, higher KVP, more scatter, field size, larger area, more scatter, and patient thickness, thicker part, more scatter.
And if you increase KVP, say from 70 to 80, what happens to the proportion of scatter interactions compared to useful absorption?
As KVP goes up, you get a higher proportion of scatter radiation relative to photoelectric absorption. Compton scatter becomes more likely. That's exactly why grids become so much more important at higher KVPs to clean up all that extra scatter.
Speaking of grids, how do we define grid ratio?
Grid ratio is the height of the lead strips divided by the width of the space between the strips, the interspace material. Higher ratio means taller strips or narrower spaces, generally better cleanup.
And the sources give some specific grid conversion examples. If you do a shoulder at 6 MAs with an 8.1 grid, what MAs do you need if you switch to a 16.1 grid for the same exposure?
Okay, going from 8.1 to 16.1, that's a much more aggressive grid. The sources indicate you need to double the MAs, so 12 MAs.
And another one, you do an exposure at 90 kVp, 20 MAs with no grid, then you repeat it using a 12.1 grid. What MAs is needed now?
Whoa, going from no grid to a 12.1, that needs a big jump. The sources state 80 memes in that case. That's a 4 times increase. Really shows you the dose impact of using high ratio grids.
Definitely. Now, what if you don't have a grid, but you're imaging a thicker part and need better contrast? What can you do, according to the sources, using positioning?
The sources suggest increasing the OID, the object to image distance, creating an air gap. A lot of the scatter photons travel at an angle, so if there's a gap, they'll miss the detector. It's not as good as a grid, but it helps improve contrast.
Good tip. What's the name of that device on the collimator that automatically restricts the beam to the size of the image receptor you've selected?
That's the PBL, or positive beam limiting device. It's a safety feature, helps reduce dose and scatter by ensuring you don't irradiate more than necessary.
Okay, geometry and distortion. What causes foreshortening? Making something look shorter on the image than it really is.
Foreshortening happens when the object itself is angled, but the X-ray beam is perpendicular to the image receptor. The length of the object isn't parallel to the receptor, so it projects as shorter.
The sources have a magnification calculation. If the magnification factor, MF, is 1.06, and an object measures 20 centimeters on the image, what's the actual size of the object?
Okay, the formula is object size equals image size, MF. So 20 centimeters divided by 1.06. That comes out to about 18.87 centimeters. The source rounds it to 18.9 centimeters.
Let's do the other calculation from the sources. What's the magnification factor if your SID is 90 centimeters and the OID is 5 centimeters?
All right, MF equals SID, SOD. First, find SOD, source to object distance, which is SID minus OID. So 90 centimeters, 5 centimeters versus 85 centimeters SOD. Then MF equals 90 centimeter, 85 centimeters, which is about 1.0588. The sources round that up to 1.06. See how it all connects.
Nice. Okay, last section. Let's talk about the final displayed image and potential problems artifacts. Once you have the digital image up on the monitor, what post-processing control adjusts the overall brightness?
That's the window level. Sliding the window level up or down makes the image appear brighter or darker.
Let's quickly list basic tissues based on the sources, from most radiolucent, darkest, to most radiopaque, brightest.
Okay, easiest for X-rays to pass through to hardest. Lung, air is very dark, then fat, then muscle, and finally bone, which absorbs the most, appears brightest. Good order to memorize for checking images.
Digital imaging is great, but artifacts happen. The sources mention a ghost image. What causes that?
Ghost images are usually from incomplete erasure of the detector plate before the next exposure. Some leftover signal from the previous image creates that faint ghost. You see this with CR plates sometimes if the erasure lamp isn't working right.
And the sources list several general causes for digital artifacts. Things like dirt, pixel failure, dust, scratches. If those were options, would all of the above be correct?
Yes, based on the sources, all of those physical defects on the image receptor can definitely cause artifacts.
The sources also talk about object artifacts, problems related to the patient or the beam setup, not the detector itself.
Yeah.
What kind of things cause those?
Object artifacts can come from bad collimation, maybe choosing the wrong histogram processing algorithm for the body part, or even just positioning the patient incorrectly. The sources list all of those. Oh, and also improper image field orientation, like if the image is sideways relative to how the processing expects it.
When the system finds a dead pixel, one that's not working, it often fills in the value based on its neighbors. What's that correction process called?
That's called interpolation. The software basically makes an educated guess for the dead pixel based on the pixels around it.
And the sources lump digital artifacts into three main categories. What are they?
The three big categories are image receptor artifacts like dust, scratches, dead pixels, software artifacts like processing errors, interpolation issues, and object artifacts related to patient positioning, collimation, etc. Knowing the category helps narrow down the cause.
Finally, that fundamental graph used in digital processing, the one showing all the pixel values in an image and how many times each value appears. What's it called?
That's the histogram. It's crucial for the computer to analyze the image data correctly and apply the right lookup table for proper brightness and contrast. You'll be looking at histograms indirectly all the time.
Phew. Okay, wow. We really did cover a lot there, hitting all those key areas from your sources detectors, the TUD, physics, factors, quality, grids, artifacts, the whole shebang.
Yeah.
It's definitely a complex system, but hopefully breaking it down like this, focusing on those core facts, makes it feel a bit more manageable.
Absolutely. That was the mission, right? To pull out those essential pieces for your RT304 review. We hit the definitions, the relationships, the rules, the stuff you really need to grasp. You should have a much stronger handle on it now.
And remember, everyone, mastering this stuff isn't just about acing the final. It's the foundation for everything you do, creating good diagnostic images safely, effectively.
Yeah.
It all comes back to understanding these principles. Every single thing we talked about plays a part.
And maybe a final thought to chew on, connecting a couple of points from the sources. We said useful information comes from transmitted X-rays, right? The ones that get through. And we also said that making pixels smaller to see more detail actually increases patient dose. So what does that tell you about the constant push and pull in digital radiography? It's always this trade-off, isn't it? Trying to capture the maximum information from those transmitted photons, see every little detail, while doing everything possible to minimize the radiation dose needed to get that information. Something to keep thinking about as you start practicing.
Definitely. Keep it in the books. Keep practicing in the lab. You've got